Start.
Hello and a very good afternoon, everyone. Welcome to EPSILON 2026. I am Sahil, Vice Chairperson of IEEE SSGST GRSS chapter.
And I'm Varun, Media Head of IEEE SSGST. We are delighted to be your host for the fourth iteration of our flagship event Epsilon 2026, wherein our main goal is to provide an organized learning atmosphere and share technical information surrounding the theme Dimensions of Discovery. Our goal through this series is to create an engaging and insightful learning environment while exploring the technological advancement that shape modern Earth observations.
Welcome, everyone. We believe that today's session title, Evaluation of Remote Sensing Sensors from Multispectral to Hyperspectral and SAR, will provide you with deep insights into how sensor technologies have evolved and how they contribute to precise and intelligent decision making in geoscience.
For today's session, we have with us Mr. Anuj Soni. Anuj Soni is a geospatial intelligence specialist and the founder of Earth Orbit, where he focuses on advancing decision intelligence through spatial data and emerging remote sensing technologies. With over 4 years of experience in geospatial domain, he currently serves as a GIS associate at ISB and as remote sensing and GIS educator at Hex Star Universe. He was also recognized as the National Geospatial Fellow 2024 at IIT Bombay. With a strong academic background in geoinformatics and geology, his expertise span across ArcGIS Pro, QGIS, Google Earth Engine, machine learning, and Python for predictive spatial modeling and geospatial analytics.
Welcome, sir. We are truly honored to have you with us today and are looking forward to an insightful and enriching session.
Without further delay, I would like to invite Mr. Anuj Soni to take over the session. Over to you, sir.
Thank you so much, Sahil and Varun, for the warm welcome that you have just shown. I'm very much interested for this particular session as well, and I will really wish each viewers within this stream is going to learn something and take ahead remote sensing as this career ahead. Yeah. Okay,
Sure.
so I'll start sharing my screen. Okay. So first thing first, whenever we talk about the remote sensing, right? So remote sensing comes with one particular terminology that is remote. Remote is something used for the distant observing or the monitoring the things and the things which is present at the remote distance is called as the remote, and when you are gathering the information from it, it's called the sensing, right? That's why it's called as the remote sensing. You are gathering the information from the part of the earth's surface but without even reaching there and without even having the content. And for this particular sense, we use satellites and UAV drones to capture the informations and such, right? And so as we will be talking about the evolution of this remote sensing, how exactly it was started, right? And how we progressed from the multispectral to hyperspectral and the SAR, what exactly these terminologies are. So we will be going to dive in this particular topics within this presentation. And before going ahead, I just want to start this particular session with one very famous quote of Albert Einstein, that is, the imagination is more important than knowledge. Because if you can imagine the things, whatever is going on, whatever I'll be saying in this particular session, you will get that imagination and then you can apply it on your knowledge, right? So now let's move ahead. As Varun and Sahil already have introduced me, so I won't take much time for this particular thing. So yes, I have like expertise in geospatial sciences and the intelligence sector. Apart from that, I have like 5+ international conference publications, and I have conducted 2 geological fields, and I have taken almost 15+ courses, and I have been like invited like more than 25, and you can say the more than 50 talks, right? So now let's dive into our topics. So first thing first, which is the fundamental of remote sensing, right? So whenever we talk about the remote sensing, it comes with a certain thing, right, that you need to understand. The very first thing is whenever you are looking at something, you are only able to see me. Let takes me as example. You are only able to see me when there is a light, right? Because the light in front of me is illuminating, and that's the reflection that you are right now seeing, the color of my skin, the color of my hair, the color of my shirt. It's only because of possible, just because of that particular illumination uh, object, right? Let's say if there is no light, right? Are you able to see me right now? I hope you are not, right? Because there is no light, but now there is a light. That's why you are able to see me. So the very important thing that we need in our remote sensing is the source of energy. So in our case, the source of energy is our sun, because it is illuminating our surface, it is illuminating our earth, right? And when this source of energy and this source of illumination are actually traveling through the our atmosphere and reaching to the earth's surface, and that interacts with the object, and again it go back to the satellite which is already orbiting within the orbit of our earth, right? So they have some certain type of sensors in it, right? And generally we are able to see the things in a more pictorial, and you can say in a colorful way. That is all because of a combination of three colors, that is the red, green and blue, as we call it as a RGB, right? RGB. So these sensors are very important so that we can understand the true color of the surface and the true color nature of the surface, right? So as you can see, the canopy is seems like a green color, and this concrete plate, or you can say the structure, is represented somewhere in the gray color, right? And the black color, whatever you can understand, right? And then once this surface is being captured by these sensors, that whatever it captures, whatever the surface it captures, it transmitted to the ground surface, that is the ground station, where the transmission and the reception of the uh, raw data being received, and then lately it is being processed just to visualize whatever the things and you can say the objects are present within the earth surface. And then lately when we use our different softwares and when we apply different algorithms to over it, so the data is being captured is now supports for the interpretation as well as for the analysis. Then we can go for the interpretation and analysis, right? That is the sixth part. And once this is done, then we can apply this particular imageries and these particular data whatever we have retrieved from the sensor is now being applied for the real world applications. It can be a disaster management, it can be a defense, it can be agriculture, it can be a urban infrastructure mapping, and so and so, right? So this is the very fundamental and the overview of the remote sensing. This is how the remote sensing is being done, right? And then when we talks about the evolution, how exactly it was started, this is a very interesting story, right? So now let's move forward. In the 1980 sorry 1858, the very first aerial photograph is being taken, right? And as this is the very famous photograph which were taken at the around the Paris city, if I'm not wrong, right? So this particular person takes the camera, okay, and captures the city photograph. And this was all possible because at that time hot balloon was at the peak. So hot balloon at that particular time was very famous, and this person captures the photograph of the whole city. And the very first time we got understand how exactly things looks like from the aerial view, right? And lately, from this particular innovation and this particular idea in 1860s, during the civil war, right? Between the Germany and USSR. So they use the balloon for the surveillance. Okay, for the surveillance they use these hot balloons where they put their cameras and captures all sort of imageries on the ground and in the border areas, so that they can understand the infiltration as well as they can understand the movement of the enemies, right? And as we move forward in 1889, so the technology being improved, so we try to put cameras on the kite. Yes, this is the progression. Yeah, so we put cameras on kite and just want to take some aerial photographs and want to understand how exactly will things looks like through the aerial view, right? And again, as we move forward, then again the innovation takes place, and then we put the camera on the pigeon, and the shutter button is being attached with their feathers. As they move their feathers, the photograph is being captured, right? So multiple photographs were taken using these pigeon aerial photography, right? And during that particular time, so all sort of world war was begin, right, around 1914s. So during that time, so the camera were like even improved and the bigger camera were used, right? So what they did, and at the same time and just before that, the Wright brothers uh, were able to got the innovation that is called the aircraft, the very first aircraft during that period of time. So the people thought during the World War One, why not we use cameras over within these aircraft, so that we can get our surveillance over the area, right? So as you can see, this is the photograph from World War One. As you can see, this person is having the very giant camera in his in his hands, and continuously looking uh, and surveillance, performing the surveillance over the ground. As you can see, they captured the photograph of the area, and this is how they understand the troop movements and all their settlements, how they are actually you know forming their what you can say, the positions and all, right? And as we move forward, right, and it was the time when the things getting more advanced, and now the resolution of cameras is improved, right? So in 1940s, when again the World War II was happened, so during that time, the camera were improvised, and now they attached camera within the aircraft. Earlier the cameras was being managed by the man which is sitting over the, or the co-pilot which is sitting on the aircraft. But now this time they try to inculcate that particular camera within the aircraft, and using that aircraft, they they manage to find a target, and with the precisionness of that, they just bombard that particular area or the enemies, as you can see. So at that particular time, the camera was actually being inculcated within the aircraft. That's why they were able to fire their missiles in that particular region, right? And as we move forward in 1971, or as well as we talk about the 1960s, so this was the very first time, because after that 1940s, after 1940s, the Cold War began. The Cold War is nothing but the race to the space. Everybody wants to build a satellite, everybody wants to go beyond the earth orbit, right? They want to visit what is being possible from the space side. So at that particular time, NASA was the one who created the first earth observation, as and you can say the sort of satellite, right? But another thing is, the very first satellite that was made by the human is the Sputnik, and that it was comes from the USSR, that is the Russia one, right? Right now is Russia, earlier it was USSR. So they created the very first the human satellite which went to the space, that is the Sputnik. And that was not a what you can say, the earth observation satellite, but this was the one, Tyros 1. is the NASA satellite, and which is for the communication purposes, television and infrared uh, purposes, right? And then lately in 1972, so the sensors and the size of satellite being increased. As you can see, the size of satellite, right, and the size of different sensors, size of different RGB sensors, right, being placed within this Landsat 1 in 1972, right? And once we gather all sort of imageries, the very first RGB image, that is the true color imagery we get, is from this particular uh, year, right? But still the resolution was the problem at that particular time, right? But in this particular race, India weren't left behind, right? In 1988, India also built their very first Earth observation satellite, and its name as Indian Remote Sensing Satellite, that is IRSS first, right? And once, as you can see, this was the satellite. And after the very good demonstration of the project, and once we get the very finest earth observation data, that is the ground surface with the higher accuracy and the very good type of RGB data sets that we have received. And later on, our government were introduce the type of tickets, like generally in post office we use tickets, right? So they released their tickets in 1991, so as a symbolic what you can say, as a symbolic gesture for the Indian remote sensing satellite 1A. Its series is a 1A, right? Remember that thing, right? And as we move forward, since we want a more robust and high resolution satellites, right, in between 1972 and 2015, there are multiple earth observation satellites were introduced over the earth orbit, right? And these are from the different series of Landsat and different series of IIRS and different other space research organizations. They have put their own earth observation satellites. And in 2015, the Sentinel 2A was introduced within the space, and it's from the ESA, European Space Agency, right? And this is the multispectral remote sensing satellite. So as you can see, there are the rainbow structure, right? So these rainbow structure is nothing but the visible range where it carries the higher resolution of imagery. And this particular Sentinel 2 provides a 10 meter by 10 meter resolution. At that time in 2015, that was the higher resolution, and everybody wants to get that particular data, right? And now the remote sensing is being improved in such a way. Right now we are getting the information of the ground with the precision of the centimeter level, right? So right now we are getting the data like up to 1 centimeter, less than 1 centimeter, right? All this sort of range is even possible from the satellite, right? So what is happening in the ground, right? Now let's talk about the different platforms for the remote sensing, right? So we have like categorize our remote sensing on the ground basis, on the airborne basis, and then the space one, right? So each and every time it's not possible to place a satellite over a space. Like if you want to do a normal or the very basic, what you can say, the earth observation, so that we use the airborne. So in the airborne we use the aircraft, right? So which have the camera mounted on its base, and it captures the earth surface, right? As you can see, this is also a plane which have the camera mounted on its base and captures the all sort of imageries from the base. And then we have the drone. If you want a very high resolution information within a shorter area, right, with a higher resolution, that you can fly, like it can goes with like 150 meter and beyond that, right? Like maybe a 200 300 meters, that you can fly a drone and get the higher resolution even in point centimeters, right? So this is how the things will look like, and as well as the height, as you can see, is associated with that, because generally satellites are being placed between 700 to 900 kilometer, that is a low earth orbit. Okay, so that's why you are able to get the higher resolution of images from the satellite. And then we have the aerial one, which generally flows somewhat around 1.2 to 3.5 kilometer, and if it is a plane and it can go beyond, then it is a 10 to 12 kilometer at the altitude of height, right? So let's move forward. So now we understand the fundamental of the remote sensing, as well as how exactly the things being captured, right? Now it's time to understand what type of remote sensing are possible, right? This is again a very important question. So it's not necessary, right, that remote sensing and the capture of the data is only being possible during the daytime. As I have already shown you the one sort of example, if there is a light, that then only you can see me, right? And if there is no light, you cannot see me, right? But that's not the case all the time. We want the information of the earth's surface even when there is a no light, because that is very important in terms of defense and in terms of surveillance, right? So what happens, so in that particular scenario, we have categorized the remote sensing in two categories. The very first is the passive sensors, and the another one is the active sensor. It's also called as the passive remote sensing and the active remote sensing. So in the passive remote sensing, no energy is required to illuminate the surface by the satellite. I'm talking about the by the satellite, right? Because satellite is capturing the photo. So generally in our mobile, we have the flashlight. So whenever we want to illuminate the surface, we turn on our flash and we capture the photo. But during the daytime, when there is all natural light present there, and so that particular duration, we do not use our flashlight, right, to capture the photograph of the person. Similar things happens in remote sensing as well. When you have the sun, you do not need the illumination sensor or the illuminator, and which can be attached to the satellite. But when there is no sunlight, so there is some active sensors which are responsible to capture the surface even in the night time, and even when there is a high cloud density over the area, right? And what are the sensor and how exactly they work, I'll tell you in our coming slides, right? But before that, let's try to understand how exactly these sensors move, right? Because earth is a globe and satellite is all revolving, right? So how exactly these sensors are being placed within the satellite, this is the very important question you must have asked it, right? So what happens, so let's say this is the satellite, okay, and it is moving in this particular direction. Okay, it is revolving around the sun, and as you can see, this is the satellite and it is moving in this forward direction, right? And this is the sensor. So how exactly it is capturing, as you can see, the scan direction is this, right? So if I'll take my pen over here, so now what is happening, so the sensor is moving like this, back and forth, like this way. Okay, so what happens, so initially it captures the surface uh, in this portion, and then again in this portion, again in this portion, and then in this portion, and likewise it completes the entire patch of it, right, while moving in a forward direction, right? Satellite is moving in this particular direction and it is capturing the data in like this. So generally it's a whisk broom type of motion. So what happens is, uh, you know the way you use your you know the broom, it's going like that only, like in this manner. Okay, So next is the push broom. Push broom is basically you are pushing the thing, right? That means if the satellite is moving in this direction, so sensor captures the earth surface in the similar direction, right? That means initially it captures this particular area, right? That then it captures this area, then it captures this second one, and then this last. Okay, so this is how it captures the area one by one, moving ahead with the direction of the satellite, right? And these are the two categories of the motion, that is the whisk broom as well as the push broom. Now let's talk about the resolution of the remote sensing. That is very important, right? Because everything depends on this. We have improve our sensors, we improved our resolution of the sensors because of this, because we want the higher accuracy and the higher resolution imagery so that we can interpret what is happening on the ground, right? So there are basically four type of resolutions, so we'll talk about it one by one. So the very first resolution is the spatial resolution. Now what is spatial resolution? Okay, so if you can see, we have four examples. So the imagery which have the resolution of 30 meter. Now what is 30 meter? And then we have the 10 meter, we have a 3 meter, and last we have a 0.5 meter. Okay, now what is that? Okay, so whenever we talks about if the imagery having the resolution of 30 meter, so 30 meter is, we are talking about the one pixel. Pixel is nothing but a one particular box, right? So if I'll tell you, whenever you zoom your photograph on your mobile phone, and when you zoom in a certain way that you reaches at the pixelate level, and then you say, okay, the pictures got pixelated, right? So that pixelated is the individual box of the image, right? So that is the dimension of the pixel, right? As I'm saying the 30 meter resolution, that means this is the 30 meter and this is also 30 meter. So the ultimately this imagery will comes up with 30 meter by 30 meter. Okay, 30 meter by 30 meter. So this is the resolution of my satellite imagery. Okay, and what exactly this 30 meter by 30 meter? That means the object present on the ground having the dimension of 30 meter by 30 meter is clearly visible within the pixel, right? Similarly, the object present on a ground with having the dimension of 10 meter by 10 meter will be clearly represented within the pixel. Similarly, the definition goes with this thing, right? As you can see, this is the image of the same area, and as you can see, the finer the or you can say the lower the resolution, you will get the high details, right? So now you see, let's say this is the 30 meter by 30 meter object, okay, on the ground, but now you can see only the one certain portion of it, right? But here you can see it is divided into like 2 or 3 pixels. Right now it is divided into multiple pixels within the range, right? And now here you will see the finest clarity of the ground truth. So this is how the things will goes, right? So it tells you about the identification of the smallest unit or the structure within the image. Okay, and as the resolution goes down, as the resolution is low, the higher accuracy that you will get. Okay, so now let's talk about the spectral resolution. One is the spatial one and second is the spectral. Now what is that? So whenever you talks about the RGB is nothing but red, blue and green, right? Or like that way. So we have 2 or 3 type of sensors. The one is the multispectral and another is the hyperspectral. So whenever we talk about the multispectral, that means a satellite is able to capture the imagery of the ground with multiple imageries having a different sensitive bands. Okay, so as you can see, there image of one single frame, right? Let's say this is the ground, this is the ground, right? And the imagery is, this is the imagery 1, imagery 2, imagery 3, imagery 4, and imagery 5, correct? So the satellite is able to capture the imagery with 5 different bands, and when you superimpose any 3 band or any 3 combination, remember RGB, right? R, G, and B. So these are 3 different bands. That means satellite can capture 3 different images. Likewise, in multispectral, the imagery or the satellite is have the capacity to capture the same area with 5 different images, and having the sensitivity or the sensitive nature with each and every band is a different. Okay, whereas when we talk about the hyperspectral, so now remember that whenever we talks about the multispectral, so it have the band somewhat around 3 to 10, or you can go up to like 15. Okay, but whereas hyperspectral are the continuous bands, having the continuous branch. As you can see, there is no breakdown, right? So these are like hundreds of bands. That's why you are able to get the curve as smooth as possible. Whereas here you will see the certain histogrammic representation, and if you join this, you will see the graph like, right? So which is not that smooth in the hyperspectral, which since it is a continuous spectrum, right? So this is what the spectral resolution is. Okay, and then we next is the temporal resolution. Temporal resolution talks about a very basic thing, right? So let's say you start observing one particular area on the day one, on the day one, right? So by what time, when you cover the entire globe and again revisit to the same area, let's say the 15 day, right? It requires 15 day to again come back to the same area, and then again it revisit on the 30th day, right? So what is the gap? So gap is the 15, right? As you can see, the gap between each cycle is the 15. Okay, so the resolution, temporal resolution of this particular satellite would be 14 to 15 days. All right, so this is called as temporal. So it talks about the very basic thing. So it's the ability of imaging the area or capture the area in over time, right? So again it talks about the revisit time of the satellite. So this is nothing but a temporal resolution. Then we have the radiometric resolution. This is the last resolution. What exactly it is? A radiometric resolution basically talks about the depth and the intensity of the satellite or the imagery, right? It generally comes with the grayscale, right? As you can see in this particular image, it is for the same area, but right now it's a 1 bit radiometric resolution. What is 1 bit? 1 bit, that means 2 to the power 1. Okay, now what is that? I'll tell you. So what happens is, that means this particular 1 bit, this power is the bit and 2 is the base. All right, and now whatever comes up, that is the two level imagery. That means the imagery that contain only two colors, one is white and another is black. Then you are not able to distinguish what present beneath it, what things is present on the ground, right? And as the resolution, radiometer resolution increases, let's go for a 2, that means 2 to the power 2, that is nothing but a 4, right? This one. So here now 4 different colors are being used for the same area. Now you are able to distinguish the things, but not as such. You need more depth and more intensity over it, right? So as again you will get the another one that is 3 bits, that is 2 to the power 2 to the power 3. Now you are able to get the information with 8 different bands, 8 different color bands. Now the image being more clear. Now as you use 2 to the power 8, that is 256 level, this is the highest one. Now the image will gives you the high definition as well as the higher information from the ground. Now you can identify each and every feature. So this is what it tells about. So it talks about the depth and it talks about the intensity over a grayscale, right? And now let's talk about the remote sensing, which actually is very important to for our further slides, right? So what is happening, as we all know, our sun is the powerhouse of electromagnetic radiation, right? And whatever the light that we are seeing right now is nothing but the electromagnetic nature of that particular source, right? So when the sun emits its energy, the electromagnetic energy, it divides into again further categories. It comes with the gamma ray, x-ray, far ultraviolet, near ultraviolet, and the visible range, right? Near infrared, far infrared, and the radio wave. Microwave and radio wave are comes under like almost same umbrella. Okay, so now we have a different atmospheric layers as well. Okay, just wait for a second. Yeah, we also have different atmospheric layers. Now let's see what things reaches to the surface and what things being trapped within our atmosphere, right? So let's talk about the gamma ray. So gamma ray, when it is coming from the our source, that is the sun, it is being trapped within the stratosphere. And similarly with the x-ray, x-ray is being trapped within the mesosphere and the stratosphere. And the far infrared is itself being trapped within the thermosphere. It cannot reach us to the surface. But the portion of near infrared is able to penetrate through all these atmospheric layer and reaches to the earth's surface. That's why we call it as the ultraviolet radiation say bachna chahiye, right? So we use sunscreens which have uv, uv type of sunscreens that we usually use. We also talk about we have the uv eye cancer happens due to the ultraviolet radiations and all, right? So that is the thing. So this is very important, that is the visible range, right? So this visible range, and because of that only we are able to see the different color present on earth. Like as you can see, the ocean is in blue color, the forest is in green color, and the forest sorry, and the desert in this muddy color and all, right? All these sort of color is only being visible just because of this visible range of electromagnetic radiation. Then comes with the near infrared. So this near infrared is also able to penetrate through all the atmospheric layers and reaches to the surface. That's why we are able to see things in nighttime as well. All right, so the heat induction of that particular object, so it comes in a near infrared. And when we talk about the far infrared, it is again being trapped within the stratosphere. And the radio wave is the wave which can penetrate through all that atmospheric layers, and again it reaches to the earth surface. And we widely use right now these radio waves. I'll tell you why. Okay, now before going ahead, we first need to understand the principle of electromagnetic radiation, right? And this particular diagram that you have been already studied in your school classes as well as the college classes in the physics. So we all know light have a two type of nature, that is particle as well as wave, right? So whenever we talks about the wave nature of the light, it comes with the electromagnetic manner, right? That means it should have the characteristics of electric as well as magnetic, right? now as you can see now as you can see, this is how the wave nature of light will travels in the space, right? So as you can see, the vertical motion represents for the electric, and the horizontal motion represented as the magnetic nature of the light, right? So this is very important to understand. Why exactly this is important? Because whenever we talk about the remote sensing, the very famous and important terminology that we use is the frequency as well as the wavelength, right? So as you can see what all sort of spectrums are coming, right? The visible ray, infrared ray, ultraviolet ray, and the radio wave, right? They all travels in a wavelength. And what is wavelength? Wavelength is nothing but the distance between two consecutive waves, right? So this is the wavelength, right? And what is frequency? Frequency is where the the number of waves can pass by through a fixed point, right? Now again, let's go back to this particular example. So what is happening here? So let's see, I'll put one point over here, as you can see, right? And now just observe within 2 or 3 seconds or a 5 second how many waves being passed from that particular fixed point, right? So the number of time these waves pass through that particular point is called as the frequency, right? In this case you can say it's a 1, it may be a 2, okay, 2 seconds. So that is the frequency of it, right? So this is very important factor, the frequency as well as the wavelength. Wavelength is nothing but the distance. It talks about the distance between the consecutive wave, and the frequency talks about the how many waves being passed through a one particular point, right? And now this is what things will look like whenever we talks about the wavelength as well as the frequency. Now here you see it's all electromagnetic spectrum, and this is how it will looks like and which application it is being used. Now whenever we talks about the gamma ray is not being used for the remote sensing purpose, since the wavelength is very short. As you can see, the wavelength is very short, so it cannot be used in the remote sensing, because it cannot gives you a higher resolution or the visible nature of light, right? Because we are only able to see objects within this range, and if the electromagnetic radiation is less than that, you are not able to see it. All right. So this is the things. So again, x-ray you again cannot see all sort of that thing. And for this, atmosphere is opaque for these wavelengths, right? As we already shown, only there are certain portion of the visible radio waves, these can pass through the atmosphere and reaches to the earth's surface. That is the thing, right? And but as you can see, there is one certain portion within the ultraviolet, right, where the atmospheric window is open, and that is the optical window, right? What is that optical window, radio window, and all these sort of things? That means these are the places where the radiation in terms of visible light, micro sorry, not microwave, the infrared, as well as the radio wave or the microwave can penetrate and reaches to the earth's surface. These are what the radio windows as well as the optical windows, right? And as you can see, these are all applications. Now here is a thing, as you can see, the radio wave have a very huge wavelength. Look at the wavelength, right? This is so huge, right? So that's why they are able to penetrate through the clouds. Even if there is a cloud, the wavelength of these particular range of the radio waves is so huge, so that it can penetrate through the cloud and it can reaches to the earth surface. So that is the main benefit of use of these radio waves, and the microwave, right? And now this is the one sort of example of how the satellite data that you will retrieve, and what type of bands that you will get, and at what wavelength that each and every wave have possess, right? Now this is one sort of example of landsat. This is one sort of example of landsat 5, you can say. Okay, so here you can see landsat. Okay, so this is the thematic mapper. Okay, this is the another type of landsat satellite imagery. So as you can see, 1, 2, 3, 4, 5, 6 and 7, what are these number? These are the bands. That means whenever the satellite captures the earth's surface, it gives you 7 to 8 images, and in this condition it gives you a 7 images. What are these 7? The very first is the B is blue. Okay, then we got the green, and then we got the red. Okay, so RGB. Okay, so and also here the wavelength is present. Now blue, green and red falls between 400 to 600 nanometer. 400 to 600 nanometer. So this is the wavelength of uh, RGB, the true color, that real true color that you will be able to see within the imagery is all possible within this range. And beyond that, near infrared will start, right? And then short wave infrared will start, and ultimately when it goes further away, it comes with the thermal applications as well. Okay, within the IR region, that is the infrared one. And then we have the Landsat 7 example with EMT. Okay, so again it gives you a RGB band 1, band 2, band 3, and then band 4, and again with 5, 7 and 6. And what is 8? 8 is nothing but a panchromatic image. Okay, so 8 band is a panchromatic. That means it only have the one single band, so it gives you a black and white image. I'll show you what exactly it is. And then we have the Landsat 8, so it gives you the 1, 2, 3, 4, 5, 6, 7, okay, 8, 9 in this particular region, that is the short wave. Then we have again the thermal one, that is 10 and 11, right? Similar with the, as you can see, the Sentinel 2 as well, right? So this is the Sentinel 2 band 1, 2, 3, 4, 5, 6, 7, 8 and 8A, then 9, 10, 11, 12. Okay, so that means Sentinel 2 is able to capture the image of the same area with the 12 different imageries. Okay, with the 12 different imageries. That means for the same area you will get 12 images, and now you have to make the combination of any three, then you have to superimpose it, then the result will appear to you, right? So let's see what are the properties of each bands. We talked about the multiple bands, right? Band 1, band 2, band 3. So what is the application of these things, right? So this is one sort of example of Landsat 8.1, Landsat 8 satellite, right? So the imagery with the band 1 represents the deep blue color, and with the wavelength of 0.43 to 0.45. Don't get confused with it. It's in micrometer. Earlier we were talking about the nanometer. You can simply convert it. Again, it will comes with the 400, 430 to 450 nanometers. All right, with a spatial resolution of 30 meter by 30 meter. And its application is, it can be used for the coastal and the aerosol study. Okay, and then we have the band number 2. It is sensitive for the blue color, right? And its spectral range lies between this, right? And it is very important for the it can distinguish soil from the vegetation, as well as from the deciduous and the coniferous vegetations, right? It also very important for the bathymetric analysis or the mapping. And then we have the band 3. It is sensitive for the green color. As you can see, this is the spectral range, again the same resolution. Now it is very important for the to understand the vegetation, right? Again we have the band 4. Band 4 is nothing but the red band, and this is what its spectral resolution is, or the spectral range, you can see. And red is very sensitive for the chlorophyll. Okay, so why it is red band is sensitive for the chlorophyll, that is the study of another day. Maybe in near future, whenever we are having the session, I'll tell you why the red band is sensitive for the chlorophyll. Yeah, anyways, then we have the near infrared, right? As you can see, this is the spectral range, and it is very important for the biomass content, right, as well as the water bodies and shoreline studies. So if you want to extract the feature of or want to do the change detection over the water bodies, in near infrared is very important. Okay, now we have the short wave infrared. This is another type of infrared, right? And this is also very important to discriminate the soil moisture and the vegetation. Okay, it can detect, or it can observe the soil, the moisture content within the soil as well as within the vegetation, right? And again, we have the shortwave infrared with the different spectral ranges. Again, it is the improvised version of the SWIR1. Okay, then we have the panchromatic, as I already told you. Since it only lies within that particular range of you know the visible one, but not exactly, since it only have the one particular band, that's why they provide the higher resolution of it, that is the 15 meter by 15 meter. So it is a single band image, and here you will get the things in very high accuracy, like you can even pinpoint the bridge, you can pinpoint the cars within the road and all these sort of things. Then we have the thermal as well, two type of thermal bands, that is TIR1, TIR2, right? And its resolution is 100 meter by 100 meter. Yeah, this is very coarser one, right? So what happens here is it improves the thermal mapping. It also helps us to understand the soil moisture, right? Whether the soil have more moisture content or the less moisture content. All these sort of studies being used with these particular bands, as well as whenever we talks about the urban heat island, right? So because we use multiple transportation systems, right? And all these sort of, it generates heats. So these heats can be easily studied using these type of bands, that is the thermal band. Okay, and now let's talk about the type of imageries, right? We talks about the multiple imageries, right? So that is one band, two band, three, all these sort of things, and the hyperspectral and the SAR. So this is very important thing to understand type of imageries. So before that, you must understand what is the digital information or the digital image, right? So we oftenly call uh, these remote sensing imageries or the satellite imageries as the digital imageries, right? Digital imageries, that means the image should contain the information, because whenever you captures the photograph from your mobile phone, it only represents you or the object. It does not have any sort of information other than that. But in the satellite imageries, there are hidden informations of the object, its nature, whether the water content is present or not within that particular area, is there a flood, is there a concrete road, or is there a kacha pakka road, right? So these satellites will help us to identify these things, but how exactly these information being placed inside it? So each and every information present within each pixel, within each pixel of the image, right? So what type of information? As you can see, if you zoom in a certain way, this is one sort of example of the Statue of Liberty. Okay, so let's say this particular, we zoomed out this particular zone, and as you can see, there are multiple what you can say, the pixels, right? And we already have talked about the radiometric radiometric resolution, right? That means it contains all sort of ranges of depth of the image and the intensity of the image, right? So as you can see, each pixels have these values, right? So the darker the portion or darker the pixel, it gets the value of 1. As you can see this, it's a version of black, that means, or the dark, that is 2. And as you move towards the whiter portion of it, you will get the value in somewhat in 256 and something. Okay, so it goes like that. So within that, you need to understand, okay, that is, the 0 is the darker one, because we should not start with 1 to 255. Okay, 1 to 255, you should not go like this. You should be go like 0 to, sorry, this is 256. So you should go always with 0. 0 is very important, from 0 to 255. And when you count this 0 as well, you will get 256, that is a 2 to the power 8, right? This is very important. And each pixel and each these information, each these numbers carries an information, the spectral information. This will help us to generate a spectral signature. Okay, and pixel is the smallest unit of the image. Each pixel, each box is the smallest unit of the image, right? So this is the thing, this is very important. So this is the digital image which contains each number, each pixels represent one number from this side, and each numbers represents its spectral signature, okay, on the ground, right? So there is one type of imagery called panchromatic, as you can see at the base. So this is one panchromatic imagery from my city called Bhopal, right? So as you can see, this is all black and white, since it have only single band, right? I already told you it only have one single band, that's why it is a black and white, right? And it generally used for the what you can say, the surveillance and the observation of the change detection things, right? And then we have the multispectral imagery. Multispectral imagery generally have 3 to 10 bands, okay, and maybe more than that, since the sentinel have 12 bands. And but it should not go beyond 15 or something, okay. So that is the thing, this is the example of Landsat 8. And as you can see, for the one particular place, we'll get different imageries, same features, same everything is same, just each band is sensitive for the different application. As you can see that this is the band 1, so it is its wavelength is this in micrometer, and its application is this, right? And this is the band 2, and this is its wavelength, and it's a sensitive for the blue, right? And this is the band 3, this is the wavelength and sensitive for green. This is the band 4, this is the wavelength and sensitive for red. Again 5, 6 and 7, okay. So this is how you will get when you download the multispectral imagery data, the Landsat 8 data, okay. You will get the bundles of images that you will be using to get the RGB, that is the true color. You always have to take the combination of three. Let's say when you use 2, 3 and 4, all these together, then you will have one imagery, and that is the true color one, okay. This will tell you the ground reality when you use these all these three imageries, band 2, 3 and 4, that is blue, green and red. And here the story will change from black and white to color, right? And then we have the hyperspectral. Hyperspectral is having the highest number of imageries from the same object or from the same site. Now as you can see, this is the typical RGB one, right? Red, green and blue. When you combine this, you will see the result like this. This is the result, okay, the true color. And when you have the multispectral, you have, let's say, five imageries, and any of the three combination will give you this thing. And this will tell you the more details as compared to RGB. RGB is normal or mobile camera photos, but multispectral will tell you the application of this particular imagery in the ground. How's the health of the crop, right? What is this structure, right? Whether the harmful chemical present around it or not, right? And when you talks about the hyperspectral, since it has more than 100 bands, that means more than 100 imageries of the same object. And when you overlay over into it, you will get this particular true color imagery. And this true color imagery having the information as more as this multispectral imagery have, right? After that, the very important is the SAR, because right now whatever we talks about the RGB, the multispectral, and what it is, uh, you know, hyperspectral, these are all passive sensor imageries. That means it required sun's illumination to get the very good picture of the ground. But for the SAR is nothing but synthetic aperture radar, right? It uses the radio and the microwave. Since it is a radio and a microwave, it does not require sun as a source of illumination, because it talks about the way, the radio signals and the microwave signals. These signals does not require any sort of illumination. And since its wavelength is so large, it can penetrate through the clouds, and it will always give you the image like this. You will never get the information from the SAR as the colorful, or as the true color. You will always get the information in that way, right? And this is so accurate and so precise. As you can see the whenever you zoom in this particular area, you can even see the tower around it, right? You can see the tower, the clear structure. Whereas if we have been like captured this particular area from the maybe hyperspectral or maybe a multispectral, you won't able to see this type of structure. But with the help of SAR, you can get these information even in if there is a huge cloud cover, right? So how exactly it works? It works like that. So it first thing first is it do not need sunlight to illuminate the surface, since it is a active sensor remote sensing, right? So what it does, like it sends because the SAR sensor is being like placed in the satellite, it is successively send the radio waves and the microwaves over the target, right? All these sort of things that you can see, these arrow, these are the radio waves and the microwave. The continuous succession of these radio waves, and whatever the reflects back and again received by the sensor, it generates an image, and that is the SAR imagery, synthetic aperture radar. Okay. And as you can see, since the visible range have its own wavelength and all these sort of band 1, band 2, band 3, SAR imagery also have different bands. And now here we call it as the X band, C band, S band, L band, and P band, right? And this is the wavelength that you can see. So if it is closer to the visible range or the near infrared, as you can see, the wavelength is shorter. But as you move in this particular direction from microwave to radio wave, the wavelength is increased. Okay. And as you can see, frequency is decreased. So as you already know, wavelength is inversely proportional to its frequency, right? So since the wavelength is increasing, so the frequency is decreasing. All right. So here you can see what happens with the X band. When we talks about the X band, what happens? So it gives you the certain sort of information of the canopy's density over in the upper regions. Okay. It tells you about the health of the tree, right? Since it can penetrate within the canopy, that is the 3 centimeter of the penetration. But when we talk about the C band, it can go beyond and it can go somewhere in the branches, right? That means within like 6 centimeter or something. And when we talk about the L band, it can go beyond that, right? And it now it can go with the bark of the tree. We are talking about the trees right here, okay? So it goes to the bark of the tree, right? And then the p wave even reaches to the ground surface as well. Okay, so this is how you can go beyond your limit as compared to the hyperspectral and the multispectral. And let's see the application of each and every band. Okay, so there is one band called Ka, and this is the wavelength of it. See, hyperspectral and multispectral was in nanometer as well as micrometer. They here the wavelength only starts with the centimeter itself, right? And it goes to 100 to 30 centimeters. See how huge it is, correct? So Ka band is basically used for the airport surveillance, right? And when we talk about the K band, it is used for the H2O absorption, like water absorption in certain cases, right? And when we talk about the X band, this is help for urban monitoring, the urban sprawl and all these sort of huge buildings. It can also help us to understand the snow and ice cover, the depth of the ice cover, right? How depth it is, right? Like that way, what is the depth of the ice cover? It can help since it is able to penetrate, right? Then with the little penetration, it can also tells us about the vegetation health and the vegetation cover. Then we have the C band. It also tells us about the what you can say, the ocean maritime navigation, right? And as well as to detect the objects within the ocean, right? The ship track, to tracking the ships. The oil fill, like when the oil is being splatted over the ocean surface, these SAR imagery is really helpful to detect these areas and for the post recovery. Then we have the S band, right? So little what you can see for this is very important for the earth observation, right? For the agriculture monitoring. And Nisar is carrying the S band, right? So can you guys tell me in the like the chat section or the comment section, what is the Nisar full form? What is the full form of Nisar, right? This is the initiation between you know ISRO as well as NASA, and we have the joint project. And we recently launched this particular satellite, that is the SAR satellite. This has the multi-purpose capability for the defense, for the agriculture, for the disaster, and for the climate change as well. Okay, so that is the thing. And then we have the L band, and this is again used for the geophysical, since it can able to penetrate to the earth's surface as well, like at least for a few centimeters. Okay, so it will help us to understand the biomass as well as the vegetation mapping with the high penetration. Again, P band is also useful for the biomass capturing as well as the vegetation health and crop health, all these sort of things, right? Now at the very last, we are at the very last of our session, that is now we talks about the application of each these things, right? So first thing first, whenever we talks about the agriculture, right? So what we want a precision farming. We using the hyperspectral, multispectral, and the SAR, right? So what happens is like as you can see within this particular image, so this is the SAR data. So when you can use the multi-temporal SAR data. Now what is multi-temporal? Temporal is nothing but the time, right? Within the different time frame, right? Let's see, you have taken the 3 time frame, and when you combine it, and then you can, and using your machine learning models or the AI models or the manual way, whatever that you can use, right? So when you run all these sort of machine learning models, ultimately you will get the soil moisture index within the ground. What is the moisture content present within the soil, so that it is very good for the crop, right? So like that way, so when you combine all these sort of imageries, that you will get these sort of results which is very help for a decision makers to create policies and to use some alternatives to improve the things, right? And another thing is using the different what I can say, the satellite indices, right? What these indices are, these are the basic combination of different bands in a certain way so that you can get the better informations, right? So as you can see, this is one sort of example, right? So this is what the area looks like. As you can see, these areas, so these areas represent as the stressed region, right, where the water content is very low, and maybe a crop encounter with some sort of disease. That's why the yellowish portion comes up within the crop, right? All these sort of things. So the key application for the agriculture is for the multi spectral one, what we use Sentinel 2, Landsat 8 and 9. You can use the NDVI, that is normalized difference vegetation index. Okay, so it tells you about the irrigation stress, yield estimation, all these sort of things. For the hyperspectral, you can use the Prisma data, and EMAP also are uh, NRSC also provide hyperspectral data that you can use, you can buy for your own application, and so it can tells you about the early disease detection, right? And the nutrition deficiency if there is any, and as well as the crop stress for different visual symptoms, right? The yellowish of the crop and the brownish of the crop and all these sort of things, right? Then we have the SAR, that you can use the Sentinel one. Sentinel one is for the SAR as well as I said, and NISAR and INSAR is also an Indian SAR satellite. Here you can use it for the soil moisture, the crop growth, and the benefit of the SAR imagery is you are not restricted that you can only able to get the data during the daytime, but during the night time as well as when there is high cloud and you want to study the flood impact, because during the rainy season there are all across cloud covers. During that time frame also you can visualize your surface, right? And then later on, yeah, you can fuse your data with the AI for the yield prediction, for identify and optimize fertilizer and water, right? And as well as the crop classification, like what type of crop is being introduced within the field, right? So it's used basically in India use case. So there is one policy called FASAL as well as PMFB. This is from the Prime Minister's initiative. We use these satellite imageries, the SAR as well as the hyperspectral multispectral, to understand the crop insurance monitoring, right? So generally during the floody region or the crop area which is affected by the flood, so all sort of insurance company needs to understand the total loss that has been happened, right? So these can be studied using the satellite imageries, right? So there is like huge improvement, like around 10 to 25% improve in yield, as well as 30% of water saving, what I can say, application is being introduced, right? And so and so. And after that we have another application that is in the disaster management. So these satellites also help us as the early warning systems. Okay, so and these remote sensing satellites and imageries help us to monitor as well as to do the damage assessments. Okay, this is very important. All right. As you can see within this region, so this is from the one sort of example of 22 August 2017. This is how the area was affected, and this is what the blue portion, as you can see, is the high affected zone of within the blue color. And now this is that from the 29th August 2017, after few days, right? And this is how the things will look like within the radar, that is the SAR imagery, right? Since we have provided a false color, that's why it looks like this. And this is how the outcome looks like. And as you can see the difference between all both these time frames. Okay, so yeah, so multispectral is being used for the flood mapping, wildfire detection, cyclone damage, as well as the drought monitoring. Hyperspectral being used for the burn severity, contamination mapping, if there is any contamination happened around the some sort of factory and all. And it also tells you about the water pollution after the disaster. Okay, then comes the SAR. It also helps in the flood mapping, since there is a cloud cover. As you can see, this is a multispectral, right? So you can see a lot of cloud covers, right? Because of these you cannot see the information present beneath it, right? Since it is all these cloud cover the the surface area. But here in this case, this is the radar one. You can know, you are like free to visualize the thing, and there is no such cloud covers, right? Since it is able to penetrate through the cloud, and it can just neglect all these sort of cloud things. But here in this portion you can see the clouds, right? Again, you can also integrate your AI for the rapid mapping and risk zone identification. What will be the potential zone where these particular flood and earthquake and all these sort of landslides can affect the region, right? So some use case for the India was the Kerala flood, the Bihar flood, the Uttarakhand landslide, and the cyclone tracking, and all these sort of things, right? So what is the impact like by using these satellites? Like the very famous is faster disaster response, because current are natural disaster authority, they regularly use these datas and provide us response faster as much as possible, right? As well as they put and improve their rescue planning using these things, like at from which area we should go, which area will be prioritized, and which area needs to be uh, settled down, and all these sort of things. Okay, and then we have the urban planning intelligence is also very important. As you can see how the area is being urbanized, and using different sort of applications and different form of indices, that you can extract the building features, the road features, and all sort of things to understand where exactly the urban sprawl is increasing, and what are the potential zones for the growth, right? For the multispectral application ways, we can use it for the land use, land cover, urban sprawl, urban heat island, as I already told you, and as well as the vegetation loss, right? As you can see, so this might be the portion earlier where the vegetation was happened, but due to the construction it has been like removed or vanished due to the infrastructure development, right? Then we have the hyperspectral. Again, it provides the material and the roof identification, whether the roof is made up of a metal or the concrete or some any other material. Okay, like it can be a terracotta tile, right? Again, it can help to monitor the pollution as well as construction material detection. And as for the SAR, INSAR, as I already told you, this is the Indian satellite that we generally used, right? So in this particular sense, we talks about the urban subsidence and the infrastructure deformation, the metro and the bridge stability. We can easily study using this particular thing. And if we apply a artificial intelligence and the data fusion, whatever the data that we get from all these sort of imageries, so it will help us to understand the pattern of urban growth, right? And you can predict the things like in near future, maybe 2 or 3 years, at which exactly the portion of the city will be grow faster as compared to the other one. And risk mapping is also very important, because urban growth leads to some sort of risk thing, let's say the storm water mapping, right? And also the sewer is the major issue, like and the urban flood is major issue due to the development, right? So all these sort of things can be automated, and all these sort things can be better studied with this particular applications. And the Indian use case are actually a smart city mission metro corridor monitoring, and the urban expansion analysis, and all these sort of things, right? Because this will improve your decision making systems, this will improve your planning, reduce infrastructure risk, as well as the cost optimization, which is very important. Okay. Then we have the climate environment monitoring. So this is one sort of example of our India region, that is the Gangotri Glacier. So the things were started. This is a time series analysis basically. So in 1780s, the glacier was found at this particular zone, but in 1849 it was here. In 1900 it was here. In 1935 it is here, and 56, and as you can see 1971 it was here, right? And in 2001 it was here. So what is happening here? So this is the glacier retreat. This phenomena is generally called as the glacier retreat, right? The glacier is being retreating, the glacier is being reducing, right? So these monitoring is very crucial and can be done by remote sensing applications. And multispectral is used for the glacier monitoring, the drought assessment, the vegetation change, and the water body dynamics, right? Where exactly water is coming from and how it is putting its hands over the area, right? And then we have the hyperspectral helps to for a carbon cycle, and vegetation chemistry, air water pollution, and all sort of economics, ecosystem health, right? SAR, as I already told you, it tells us about the ice thickness and biomass and the wetland monitoring, right? And with the again with the integration of AI, what it does, it does very simple, understand the climate trends, what exactly happens through the past over years to that cycle, how the climate is being changed, and how the area is being affected uh, with the same scenario, and all these sort of things, right? It helps us to understand the prediction level study. And then for the Indian case, as I already told you about the Gangotri glacier retreat, so this is called as the retreat one, right? And we can also study the forest cover mapping, how the deforestation is being happened, and if the Indian forest cover is being increased or decreased, and what is the exact scenario, right? All these sort of things. So its impact is basically to support the climate policies that we generally making within our country. And then again, we should talk about the sustainability planning, how we are going to create a sustainable plan using these observation, using these data for the betterment of the humankind and betterment of the Indian people, right? All these sort of things. Again, so last but not the least, this is for the defense strategic geospatial intelligence, right? So this is one sort of example, the recent conflict between Russia and Ukraine, right? So as you can see, the Russian troops were actually settled over here, and this is the imagery were taken from the SAR imagery. Okay, so this is the uh, NASA satellite, which is having the capability of the synthetic aperture radar. And as you can see, these are some border areas, and near the border areas you can see the movement of troops and their vehicles and all these sort of deployments. And these SAR imageries is able to identify all these sort of things. So this is how it is used in defense and all these sort of things. And even in Operation Sindoor recently, that uh, our defense force provide each and every evidence based on the satellite imageries and based on the drone imageries, right? This is where we have gone, this is what we have done, and all these sort of things. Yeah, anyways, for the multispectral studies, it can help us to study the terrain mapping, for the border monitoring and the infrastructure tracking. Then for the hyperspectral, it will help us to identify the detection of the camouflage, because generally enemies use camouflage to hide themselves within the dense forest canopy, and all these sort of desertic areas. And so, and the material identification, whether it is a rubber, whether it is a metal, and whether it is a cloth, and any sort of other materials that is hidden behind, right? And then we use the SAR, since it is a all weather day night surveillance. So we regularly use SAR imageries. Okay, and again it helps us to track the ship and vehicle detection as well, and the terrain deformation monitoring, like if the terrain is being deformed due to some sort of activity, or maybe some bunker buster bombs, and so and so, right? And then we have the artificial intelligence integration. Again, this will tell us how to automate the target detection, right? So these satellite will automatically target, let's see, this is the example itself, like you identify the things and you log the things, and then you just deploy your, since it is your target, then you can deploy your bomb and whatever it is. And threat monitoring and situational intelligence, like whether they are moving in that direction or moving in that direction. If they're moving in that particular direction, what precautions we should take, and how we can retaliate over that, this in for this purpose. For the Indian context, like if we talk about the water surveillance, this remote sensing is very important for the maritime monitoring and for the strategic reconnaissance, right? So this is very important, and impact it is making, so enhance the situational awareness, right? This is very important, and this is what we used in our operation Sindoor as well, right? Faster decision making as well as the strategic advantages, right? So this is how we use all sort of imageries, different imageries with the different applications, and in the different sectors, right? So this is the reference, certain reference for this particular presentation. And thank you so much. And at Earth Orbit, I want to introduce Earth Orbit as well. So Earth Orbit is basically and geospatial intelligence risk assessment firm, where we do the very similar applications that you have just seen within my presentation. And we do a lot of GIS as well as geospatial and the remote sensing stuff. We provide the applications and the result oriented solutions, which will be beneficial for the industries, PSUs, and the government. So yeah, that's all. Thank you so much for the grass team as well. So now I'll hand over to Sahil and Varun. I'm done with my presentation.
What an insightful and enriching session it was. Thank you so much, sir, for taking us through the fascinating evaluation of remote sensing sensors and helping us understand how these technologies enable precise Earth observation and smarter decision making.
Yeah, please come again.
Thank you so much, sir. So moving ahead, we will now begin a quick Q&A session. If you
Yeah,
have any
definitely.
questions or doubts related to today's topic, feel free to post them in the chat box. Sir, you can check the comment sections. There
Yeah,
are
yeah.
questions.
There are a few questions from Ayush, Mr. Geese, Tana.
Yeah, Mr. I see Girish, correct, this particular question, right? So I totally agree with you. Like we can downstream our image resolution using the Google Earth engine. And recently we also have tried the similar thing within our organization, that we use the 30 meter by 30 meter resolution, and we downstream and downscale to up to a 10 meter by 10 meter, right? This is our very first priority, and now we are trying to even downscale it further to maybe a 5 meter by 5 meter, so that we can keep the things as stagnant as possible, but the information whatever we are getting is very uh, it should not downgrades the information, right? That is the main that thing that we are maintaining in our organization. So I'll totally agree with you. We can definitely use Google Earth Engine, Python, as well as the R. So we generally use R as well. Yeah. Yeah, definitely. We have more than 24 bands and up to 256, even beyond that as well, because I have encountered with certain uh, datas. So I'll talk about the average data. Average data has somewhat around 625 bands, right? As now you can imagine 600 and bands. So its data is huge. So you have to use the each and every band very wisely, and it gives you immense level of informations, right? So that is the thing, we use it for a soil texture analysis. We map the soil texture based on these hyperspectral informations, right? That is the thing. So I'll totally agree with that. And again the thing is yeah, I totally understand why your thing that is a spatial resolution, because since these things cannot be, you know, gathered and restructured within 15 days. That is the typical what I can say, the temporal resolution of sentinel 2, the sentinel 1, if you're talking about, right? Even the hyperspectral is not being provided to publicly that oftenly. And if we are, I'm talking about the prisma also have one limitation, that is the temporal resolution, right? Otherwise the data is good to go. Yeah. What are the major challenges faced while collecting accurate sensor data in real world environment? Okay, so there are certain challenges that we have encountered. So the very first, because in remote sensing we have a session called uh, error. Okay, error matrix. So in within the error matrix, there is a calibration issue, right? There might be sensors, so their sensor might get affected due to its orientation, and due to in a space there are certain conditions happen. So it is very important to recalibrate these data on the ground before it is available for us, right? So that's why the process called a pre-processing, the pre-processing is performed within the organization who is actually retrieving the data, okay, from directly from the satellite. So there is one sort of error that you might have heard of, that is the stripped base error, as well as the paper salt error, right? This is also due to the some sensor misinterpretation, as well as some environmental effect is also very important, right? That is the haze error is very common uh, due to some sort of what I can say, the unrelatable and unexpected environment within the space region around the sensors and the satellite. So these haze come across in these sort of things. But to tackle that, we also have created the solutions for the same, right? That is called as the error correction capabilities, right? So these are being performed within the ground stations when they are pre-processing the data, and then only they'll make it available for us to use. Yeah. Okay. Interested in remote sensing and geoscience, what foundational skill or subject should they focus on first? Okay. First, if you are starting with your career in geosciences, first you need to understand the nature of the geosciences. What I can say, the geology. If you are talking about the geology, you need to understand first the geology of the nature. Okay, how it is made up of, what characteristics it represents, and how exactly it will be looking from the satellite perspective, imagery perspective. And then lately you can switch it over the remote sensing once you have the basic knowledge of the ground, right, or the geography, right. Then only you will be able to utilize your previous geostatical and the geographical knowledge over the remote sensing. Since remote sensing is all technical based field, and the only skill is required as the interpretation. The better you interpret the things from the satellite perspective, then only you can apply it over the geosciences and any other sort of real world scenario. So I rather recommend you to first grab the enough knowledge from either from the geography, from the geological sciences, then you can use remote sensing as an application for the same. Yeah.
So that brings us to the end of the question and answer session. Sir, we would like to present you with a small token of gratitude as a gesture of our appreciation. We are
Yes.
truly grateful to you. Our participants surely gain valuable insights into the evaluation of remote sensing sensors and their real world applications.
Thank you so much. Thank
Thank
you
you.
so much.
Yeah. Thank you once again for joining us, sir. We learned so much about the transition from multispectral to hyperspectral system, the working principle of SAR, and the comparison between optical and radar sensors.
So lastly, we would like to thank all of you for being such an attentive and enthusiastic audience. We hope today's session gave you a clear understanding of how evaluation sensors technologies are shaping the future of geoscience and remote sensing.
Hmm.
We will look forward to seeing you in tomorrow's session. Thank you and have a great day.